Okay, so for screencast number 10, I had it done a few times and just got frustrated and gave up on it. So I decided just to finish it and go with what I have. So here we go. This is the end. Several objects of various disk, spheres, solid, and hollow are the row down a ramp, which is sitting on a table. Which object will fall the furthest from the table? Determine how changing the mass and the radius will affect the change of distance away from the table that object falls. So one big thing that we need to know is that the larger the momentum of inertia is, the smaller the speed, v, and less energy. So the smaller the speed, it's not going to go as far. So the larger inertia, it's going to go not as far. The less inertia, it's going to have more energy and it's going to go farther. So I did 1, 2, 3, 4. No, it said disc, sphere, solid, and hollow. I figured it said disc, like hoop, hollow, and a regular disc, a solid sphere, and a hollow sphere. That's just what I figured it meant. So I figured all the inertias of each one. Inertia of a hoop, inertia of a sphere, inertia of inertia of a hollow sphere, inertia of a solid sphere, inertia of a hoop, and inertia of a disc. So who will go furthest? So rotational and we have rotational and translational kinetic energy. Okay, in this case we have this. OK equals 1/2 mv squared plus 1/2 inertia omega squared, but we could follow this to find the total kinetic energy, and we know that the kinetic energy in the beginning is going to equal the kinetic energy at the end. But in order for us to find which is going to fall furthest, the only thing we really need to focus on is inertia, and what inertia is. So I just tested it by giving it the same mass and giving it the same radius for each exact object. So each one, I just pretend that they have the same radius and they have the same mass. So I solved it with 0.5 kilograms and 0.15 meters of the radius for each one. And I got for the hollow sphere, I got 0.0075 kilograms per meter squared. For the solid sphere, I got 0.0045. For the hoop, I got 0.01125. And for the disc, I got 0.0562. This is really good because this is what inertia equals, okay? This is each one of the inertials within the same mass and the same radius. So I wanted to know which one's going to go furthest. So we know that the one with the largest momentum has the least speed. So the one with the largest momentum is going to be this one. Wait, no, that's this one with the less. The one with the largest momentum is going to be this one. So the one with the second largest momentum is going to be this one, 0.0075. Now with the third largest momentum, it's going to be 0.0056, and then it's going to be 0.0045. So then I just ordered them from which one's going to have the greatest. So obviously the one with biggest inertia is going to have the least. It's going to go the short amount. The short amount of distance. So that's this one has the most. And then the solid sphere has the least inertia, which is going to win. That means it's gonna have more energy and more speed. So then I just did it up here. So in my case order, I did the solid sphere is gonna win. The disc is gonna be second because it has the second least. And then it's gonna be the hollow sphere. Then it's gonna be the hoop. It's gonna be last, depending on the inertias. So then, so the solid sphere will go the furthest. So then I said, well, what do you know when you change the radius and the mass of an object? So, start at rest, and I did a whole bunch of other stuff. Again, I brought up the kinetic energy, but I figured it's not even what I need, so I kind of ended up testing it right here, okay? I went with, so let's say that they have the same speed, so I could do it that way, but I decided not to. I decided to still work with inertia and just plug in different digits. So, example, I just did example to prove what I mean. example, I doubled the mass for each one, okay? So for instance, we have here, so for the hollow sphere, I doubled the mass and I did it 0.1 kilograms. When I solved for that, I got 0.015, okay? And that, in this case, was second place, right? Now, when I give it 0.015, when I look at all the ones that I had, when I change its mass to double, when I look at 0.015, it's going to be greater than the last. So this is going to end up being last if I change the mass. Same with each one. So if I just look only at the solid without looking at these two, if I double the mass, it's going to equal 0.009. And in this case, this was our number one. It was 0.0045 was the least inertia. Now here, it's a lot of greater inertia, okay? So this is going to be like the last one. So I figured that and I did that for each one just to prove it. Then I doubled the radius as well. Instead of doing 0.15 meters, I did 0.2 meters. And I kind of did, I did that one. I compared it to the ones that I have, which place it would be. I compared the solid sphere, then compared the hoop, which place it would be. And I kind of experimented with numbers. So I came into the conclusion the increase of mass of the object will increase its inertia. So the increase of the mass will increase its inertia and will slow down the object. And then the increase of the radius will also increase inertia, which will also slow down the radius. The less of a radius and less mass will increase inertia and will make it go farther away. Okay? It will make it go farther away. It will decrease inertia. It will make it have more energy. So that's what I came up with this answer.